Imagine stepping inside a cavern of riveted steel at dawn. Breath fogs in the air like a ghostly registration of each worker's movement. The warm cloud of exhalation meets cold metal and turns to visible proof of labor. Rivet guns staccato across the bay, a percussion orchestra that never quite finds a comfortable tempo. Crates marked with part numbers sit like silent columns of possibility. Engines waiting like sleeping beasts, sacks of bearings and handfuls of rivets, pallets of .50 caliber ammunition stacked in neat, stoic ranks. For the camera, for the record, for anyone who tries to understand how raw materials became a tactical answer on the battlefield, this place, the assembly bay, the tool room, the stretch of concrete where men and women leaned under wings, is the story's starting point. We call it inside the frozen factory as a shape for the imagination. That phrasing is an evocative reconstruction. It asks you to feel cold breath, the shimmer of steam, the gloss of metal under a dim winter light. The archival record does not allow us to pin an exact temperature to these bays, and good history refuses invented certainties. But the image is purposeful. It anchors everything that follows: the smell of oil and heated rivets, the way a worker's glove fogs when moved from heated skin into the open air of a large hall, the sound of an engine part being lowered into a cradle. Think of that coldness as the atmosphere in which something enormous took shape, a machine designed to rewrite the air war, assembled piece by painstaking piece. What left these bays and changed the course of air combat was the Republic P-47 Thunderbolt. Between 1941 and the war's end, factories under Republic Aviation and their subcontractors produced 15,683 Thunderbolts. At peak output in Farmingdale, Long Island, the lines turned out roughly one full P-47 per hour. Evansville, Indiana, a city remade into an industrial artery, was producing up to 500 aircraft a month by 1944. Those numbers are not just impressive, they are strategic. Every aircraft that rolled off a line represented tens of thousands of parts assembled to exacting tolerances, miles of wiring threaded through narrow bays, and thousands of hours of human labor transformed into a single flight-ready machine. A single Thunderbolt was astonishingly complex on the production floor. The transcription of wartime records cites approximately 65,000 individual parts required to build one airplane. Wiring alone totaled nearly 8 miles per aircraft when stretched end to end. Each airframe used on the order of 2,000 pounds of aluminum. These are not poetic figures. They are the arithmetic of the industrial age applied to war. Multiply them by thousands, by weeks of relentless assembly, by the months that converted farmland and factory space into a continuous flow of metal and muscle, and you begin to see the logistical behemoth behind every sortie. And the logistics did not end at the airframe. Each Thunderbolt carried a weight of weapons and ammunition that turned it into a flying depot of lead. 8.50 caliber Brownings were standard armament on many P-47 models, and at standard loadouts, the aircraft carried roughly 3,400 rounds, 8 guns with about 425 rounds per gun. The Lake City Arsenal, that vast government plant dedicated to small arms ammunition, produced on the order of 30 million rounds a month during peak wartime output. Ammunition, fuel, spare parts, engines. The supply chain had to be as relentless as the assembly line itself. The 9th Air Force, as wartime dispatches and logistics summaries record, sustained intense sortie rates and consumed prodigious quantities of ammunition and rockets to support tactical air operations in the European theater. Records noted heavy rocket and ammunition usage across their campaigns. These figures are the hard arithmetic that underpins strategy. When you could make replacements faster than the enemy could destroy them, attrition ceased to be decisive in the old way and became instead a war of industrial endurance. Walk the floor and the production story becomes human. Workers were pressed into service by necessity. Men in uniforms, older men and teenagers, and a large and growing number of women answering the call to keep the machines turning. Entire cities were repurposed. training programs accelerated. People learned to do with speed what had previously taken years of apprenticeship. The wiring harness that would feed systems down the fuselage, radios, guns, ignition, had to be bundled and laced with exact loops. A missed splice could mean radio failure at a critical moment. Machines that stamped bulkheads shouted and spat steel. Riveters stood shoulder to shoulder, eyes on the seam and hands steady as surgeons. The manufacturing story has small scenes that, when stitched together, produce a larger truth about American war production. A young woman who had never touched a rivet gun before March of 1942 could, by the fall, be trusted with the fuselage skins on a production run. A machinist who had replaced a father in a local plant found himself calibrating throttle linkages for a turbocharged engine. Crew chiefs coming from the front would later speak of the quality. The attention to armor, to fasteners, to redundancy meant that these planes could take punishment and keep flying. That reliability became part of the Thunderbolt's reputation, but it began in these pragmatic, domestic spaces where training, supervision, and the division of labor were tightened into a wartime cadence. Yet, if the factory floor supplies facts, it also supplies sound. Editors of wartime newsreels, and the memory of those present, often pointed to the rhythm. The constant percussion of rivet guns, the low hum of milling machines, the occasional roar as an engine was run in, and, above it all, the soft, steady presence of human voices guiding and correcting. Cross-cut that with the acoustic memory of P-47s in flight, engines building to a roar that swallowed conversation, and you can begin to appreciate why aviators and mechanics sometimes used the same verbs to describe both: thunder, pound, and sing. Sound, in this story, is part of the linkage between factory and sky. The majestic scale of production, one plane per hour at peak, thousands per year, reshaped not only material availability, but doctrine and morale. Early in the war, the concept of quality over quantity still held sway among many tactical thinkers. Smaller, more maneuverable fighters that could outturn an enemy in a dogfight had long been thought the apex of air combat. The Thunderbolt, with its bulky fuselage and radial engine, was initially mocked in some circles for its size and a perceived lack of agility. But the factory output meant something else. This machine was designed not for turning with a Messerschmitt at close quarters, but for diving, for carrying heavy armament, for absorbing hits, and for being replaced faster than the enemy could afford to be. Over and over, the assembly bays would produce aircraft intended for tactics that had yet to be fully embraced by doctrine. Inside those assembly bays, design choices that looked awkward on a drawing board took on the sheen of inevitability. The P-47's Wright R-2800 double wasp radial engine, turbocharged in many models, dominated the nose and required novel mounting, cooling, and supercharging systems. Armor plating around the cockpit and engine mounts added weight but increased survivability. 8.50 caliber machine guns, wired and bolted into synchronized mounts, gave a P-47 a breadth of firepower that could be measured in the tearing apart of both aircraft and soft ground targets. Convergence settings, the geometry that allowed guns to focus their fire at a set distance, had to be set with precision for the weapons to be effective. Those adjustments were, quite literally, part of the final checklist on the line. The factory's output was not only a question of numbers, but of repetitive quality. The process of proving an aircraft ready for combat required a series of bench checks, engine tests, balance verifications, and a final run where a mechanic would listen to the engine, check for oil pressure fluctuations, and note the vibration signature. Any sign of abnormality could send the plane back down the line for rework. That rigorous attentiveness was part of the reason a P-47 could, after absorbing damage, often limp back to friendly territory where ground crews could rebuild what was broken. And yet, the skill and persistence of the factory floor were only half of what transformed the Thunderbolt into a weapon at scale. Behind the assembly line, the machinery of procurement, the arsenal outputs, and the shipping networks fed the lines continuously. Engines from machining plants, propellers from specialized subcontractors, fitted and certified. Ammunition from arsenals like Lake City flowed in steady quantities. The decision to standardize parts where possible, to manufacture on a mass scale, and to keep supply chains fluid made the difference between production as boutique craftsmanship and production as strategic instrument. Small human rhythms developed in the factories. There are archival notes and later recollections of crews tagging completed aircraft with small tokens or pins, of workers leaning to watch a completed fuselage roll past their workstation, of brief applause when the 100th or 500th plane came off the line. That camaraderie was not sentimental, it was functional. A crew that trusted its neighbor to lace wiring correctly or tighten the last torque bolt would not hesitate to operate together under pressure. Training programs emphasize these bonds, converting everyday men and women, sometimes rookies fresh from the draft board or from home, into finely tuned teams. To understand the machine, you must briefly understand what it contained. The thunder in the P-47's name was partly literal, the power of a 2,000 horsepower radial engine that, when combined with a turbocharger, allowed for sustained high-altitude performance far beyond what many expected from a single-engine aircraft. That turbocharger, an engineering answer to the thinning air at altitude, required intricate ducting and cooling and was one of the more complex assemblies that showed up at the factory. Armor plating enclosed the cockpit and critical systems. The landing gear had to be robust enough to absorb hard landings after strafing runs. Weapon bays required solid mounts and a feed system that would not jam, even under the heat of continuous fire. At the same time, the P-47's mass, often criticized at first glance, became an asset when tactically understood. The aircraft could carry external fuel tanks and, in modified variants like the P-47N, extended range tanks that allowed missions over the Pacific's vast expanses. It could mount rockets and bombs for ground attack missions, transforming the fighter into a multi-role asset. The manufacturing floor had to adapt to these variants. Some lines were retooled to accept different wing assemblies, others to produce strengthened wing hardpoints for rocket rails. That adaptability in a factory, the ability to switch tooling, to produce variant parts under time pressure, was a logistic advantage that the Axis powers increasingly found difficult to match. All of this, the parts, the gun mounts, the armor, the turbocharger, coalesced in a particular visual moment on the line, the engine install. The Wright R-2800, a broad, rumbling cylinder, arrived as a heavy, tightly chaperoned piece of hardware. Men with sweat-streaked faces and grease-blackened hands would lower it into the mount while other crews aligned the cowlinks and attached the plumbing for oil and coolant. Final checks for seals and clearances had to be meticulous. A leak in the supercharger line could mean flame-ups at altitude. On the other side of the line, armament crews were torquing gun mounts, running belts through feed chutes, and fitting sink links so that fire would hit where the pilot aimed. An accidental misfeed could cascade into a failed mission, but this was where collective discipline on the shop floor paid off, where repetition, documentation, and attention to detail converted thousands of man-hours into a flying weapon. Even with all that rigor, the human cost of this production was not abstract. The factory demanded not just skill, but endurance. Overtime became common. The steady strain of attending to tiny details in such a vast assembly line produced fatigue, and mistakes were always a risk. Safety measures existed, but were often balanced against the pressure to meet quotas. This tension between speed and caution, between output and individual well-being, was part of the moral arithmetic of wartime production. Workers were aware that their labor had immediate, lethal consequences in the theater of combat. That knowledge sharpened focus for some and war on others. If the factory is a theater of craft and supply, the pilot's cockpit is where the consequences become immediate. The Thunderbolt's design choices, weight, power, armor, firepower, made for a machine that could be adapted into a new kind of air combat doctrine. Early engagements revealed surprises. On April 8, 1943, in one of the formative early encounters recorded in operational logs, the Thunderbolt's capabilities drew mixed reactions from both Allied and Axis pilots. The aircraft's diving speed and ruggedness were not yet fully exploited by P-47 pilots, which initially left room for skepticism about its dogfighting potential. But design attributes that looked like drawbacks on paper soon proved to be battlefield assets when tactics evolved to suit them. Pilots themselves, when interviewed later or quoted in logs, told a story of adjustment. The Thunderbolt's mass made it slower to turn, but its acceleration in a dive, its ability to convert potential energy into kinetic speed, was extraordinary. Pilots learned to trade turning battles for altitude and speed. Climb, dive, strike, and climb again. This boom and zoom approach allowed Thunderbolts to make contact on favorable terms, use their heavy armament to devastating effect, and then withdraw before the enemy could exploit a turning disadvantage. Some pilot stories illustrate these tactical adjustments with human immediacy. Robert S. Johnson, later one of the unit's celebrated aces, had an early brush with near disaster that, in hindsight, reads like a turning point in how the aircraft was valued. On June 26, a date that shows up repeatedly in combat logs, Johnson returned from an engagement at Lazo in a plane that bore the testimony of enemy fire, holes through the fuselage, torn skin, but an airframe that held together enough to be flown home. His crew chief, counting damage afterwards, reportedly logged upwards of 200 holes in the fuselage and control surfaces and still found the plane repairable. Anecdotes like this fed a growing narrative, not invincibility, but a resilience that let pilots survive what might otherwise have been fatal encounters. These instances did not come free of cost. They came with trauma, with lost comrades, and with the grim arithmetic of repair and replacement. But they also supported a practical argument. The Thunderbolt could be repaired and returned to service, and more remained in the pipeline thanks to the factories. At the same time, the factory's capacity created an ever-present strategic overlay. Consider Operation Bodenplatte on January 1, 1945, a surprise Luftwaffe strike designed to destroy Allied aircraft on the ground. Even where the attack found success and aircraft were reduced to burning husks on airfields, the industrial system responded. Replacement aircraft arrived with astonishing speed, sometimes within 48 hours to fill depleted flight lines, testament to the factory's strategic buffer. To the pilots on the ground and the commanders trying to maintain air superiority, that buffer was as significant as any tactical innovation in the field. But the story of replacement is also the story of logistics. Engines shipped across an ocean, propellers balanced and tested, ammunition cases packed and palletized, and crews trained not only to fly the machines but to maintain them. A factory, therefore, was not an isolated plant. It was the central node in a global network of supply, training, and distribution. The P-47's presence in both the European and Pacific theaters exemplifies this connectivity. Variants like the P-47N, equipped with extended range capabilities, were specifically adapted for the long overwater legs of the Pacific. That adaptability required product engineers, revision to production jigs, and a constant conversation between frontline feedback and factory modification. And yet, even as the Thunderbolt's numbers grew and its battlefield role hardened into routine, skepticism lingered in some quarters. The Luftwaffe, for a time, dismissed the aircraft as a lumbering brute. Captured German pilots and intelligence reports early in the war sometimes reflected that mockery. But by the mid-war years, the mood changed. Anecdotal German reflections and post-war accounts by figures like Adolf Galland hint at a reevaluation. The P-47 was not a graceful dancer, but it was effective in ways that mattered. What changed Eisenhower's or a squadron commander's calculus was not a single dogfight, but the accumulation of losses that could not be easily replaced by the Axis, both in material and in the pilots to operate them. The industrial weight of the Allies, amplified by factories like those in Farmingdale and Evansville, was a strategic force multiplier. This is part of what the factory taught. In industrial warfare, redundancy and replaceability alter the value of risk. The Allies could accept the loss of aircraft in exchange for wider operational gains, because the assembly lines would, in time, replace them. That calculus forced doctrinal shifts, recalibrations of risk, and new operational tempos. It was not a clean equation. It involved human lives, exhausted crews, and the slow attrition of pilots who were harder to replace than planes. But in raw material terms, in spares, fuel, and ammunition, the balance increasingly favored the Allies as the war progressed. By the time D-Day arrived on June 6, 1944, P-47s were part of a layered air umbrella that had been built as much in factories as in training fields. Hundreds of Thunderbolts were committed to the invasion airspace, strafing transport and support vehicles, suppressing enemy positions, and providing close air support in a way that combined the aircraft's heavy armament with numbers. Those numbers, thousands of parts, miles of wiring, tens of thousands of rounds, translated into suppression and opportunity for ground forces. The factory's rhythm found its echo in battle, a sustained cadence that, cumulatively, reshaped a theater. If the factory is the origin point, then the stories that travel from there to the front lines, the tales of damaged aircraft that return, of repaired wings being slotted back onto serviceable frames, of electricians who work through nights to replace harnesses, are the threads that bind manufacturing to the strategic outcome. This binding is visceral. The same hands that set rivets into a skin also steady pulleys that guide a parachute into a hangar, that load ammunition belts, that later in the theater patch a combat-scarred fuselage with tape and ingenuity until a safe return can be made. One creative modality of the war's industrial story is that of adaptation. Factories learned to retool. Engineers adjusted pre-war blueprints to wartime exigencies. Alexander Kartevely, the principal designer behind many of the Republic designs, pushed ideas that culminated in an aircraft optimized for speed, power, and survivability, sometimes at the cost of elegance. Kartevely's name comes to us in various documents with minor spelling differences in the transcription, a reminder that historical records are often rough drafts of memory. Still, the essential fact remains. Design decisions originating in sketches and stress calculations had to be translated into repetitive, reliable shop procedures. That translation was neither automatic nor guaranteed. It required management, discipline, and the constant feedback loop of field reports and factory modification. By the time the line handed over a completed P-47, three separate economies had cooperated: the metal and machine economy of industrial fabrication, the human economy of labor and skill, and the logistical economy of supplies and transport. Combined, they produced an instrument of war capable of imposing new costs on the enemy. But the real test of that instrument's worth would be in combat, where the Thunderbolt's size, weight, and firepower would meet an enemy who had not yet come to terms with industrialized replacement. We leave the assembly line now, but not the factory. Picture a Thunderbolt, fresh from final checks, its skin scrubbed, its cowling secured, its guns loaded and tested with precisely the number of rounds the line specified. The plane taxis, the engine builds, the sound swallowing the bay's residual percussion. Ground crews wave it out to the tarmac, where, beyond the perimeter fence, the sky is waiting. A vast, indifferent theater that will not know, and yet will be shaped by, the thousands of hands that made this moment possible. If this kind of deep dive into the machinery of war, the factories, the people, the numbers behind the planes, is the kind of history you want to see more of. Subscribe for more. There are whole stories tied up in bolts and wiring looms, in the lives that learned new trades overnight, and in the quiet logistics offices that sent crates across oceans. Beyond that gate, the first sorties were already being planned. Missions that would take the P-47 off the airfield and into a set of engagements that tested everything the factories had made. Pilots who had barely learned the machine would soon discover how to coax advantage from its power. Crews would learn to count the cost of engagements, and tacticians would begin to reimagine air combat in a world where replacement was possible. The Thunderbolt story is only beginning to open, from the frozen, evocative dusk of the assembly bay out into the blue and the burning fields beyond. The first real tests came not in textbook exercises, but in the uncertain space of combat. On April 8, 1943, operational reports recorded an engagement that forced both sides to reassess assumptions. The Thunderbolt's raw attributes surprised observers. In a dive, it gathered speed like a freight train coming off a grade. Its structure shrugged off damage that would have torn smaller fighters apart. But pilots had to learn to use that mass as an asset, not as a liability. The doctrinal pivot, climb to altitude, strike with speed, and escape with climb, did not occur overnight. It was hammered into practice through trial, loss, and adaptation. Robert S. Johnson's near disaster at Lhotso on June 26 became one of those sharpening stones. When he brought his plane home, the fuselage looked like a sieve. Holes counted in the hundreds by the crew chief who inspected the ship. Yet, where lighter designs might have failed, the Thunderbolt's construction provided a margin for survival. The airplane that still screamed down the runway under its own power became a kind of proof. A machine that, while costly, kept a man alive and an airframe repairable. Those repair bays, fed by steady lines back in Farmingdale and Evansville, could restore a battle-scarred Thunderbolt to flying condition. The industrial cycle turned damage into repair, loss into return. The moral calculus of the war shifted accordingly. Lives were not infinite, but metal and parts could be restored at a tempo the enemy struggled to match. Francis Gabby Gabreski, already an established name among Allied pilots, encountered his own tests with the Thunderbolt. He and other aces learned to treat the aircraft as a different instrument, not for close, twisting duels, but for calculated bursts of violence and retreat. Gabreski's experience, like Johnson's, shows a pattern repeated across squadrons. Success came when pilots altered their mental models of dogfighting to favor energy tactics. The Thunderbolt's 8.50 caliber Brownings, fed by belts and fed through carefully staked mounts, delivered concentrated bursts that could shred an enemy's control surfaces or ignite fuel tanks with ruthless efficiency. Gun camera footage, the grainy, rock-hard evidence of air war, captures the moment when an approaching axis of metal and lead meets the thin skin of a German fighter, and the consequences unfold in a spray of fragments and flame. Those images were not merely spectacle. They were operational proof that a heavy, well-armed fighter could exact a toll at range and then recover. One of the clearest tactical evolutions was the widespread adoption of boom and zoom. Instead of trading turns, Thunderbolt pilots climbed above the fight, dove through with terrifying speed, let their firepower do the work, and used the aircraft's structural advantage and power to escape back to altitude. In practice, this required discipline. A pilot had to resist the old reflexes of closing into a turning engagement and instead choose when and where to strike. The factories never taught tactics, but their product shaped them. Each Thunderbolt that roared off the line carried the potential of this new doctrine. And with each mission, the strategy deepened into orthodoxy. If air-to-air engagement demonstrated certain truths, it was the Thunderbolt's ground attack role that revealed perhaps its most decisive strategic utility. Once equipped with rockets, bombs, and heavier external stores, the P-47 became a feared jabot, a fighter-bomber capable of delivering focused devastation on troops, convoys, and infrastructure. Normandy provides a striking example. On June 6, 1944, the invasion airspace was layered with aircraft of varying types. But the Thunderbolt's presence was significant not only because of numbers, but because of what those numbers could do on the ground. Fields of vehicles were strafed, artillery positions suppressed, and transport columns disrupted by concentrated attacks. The effect was more than immediate destruction. It was the grinding away of mobility and morale. Those ground attack sorties were thirsty for logistics. A single mission could burn through hundreds of rounds per gun and expend rockets that had to be produced, shipped, and issued in great numbers. Here, the arithmetic of industry asserts itself again. The Lake City arsenal turning out millions of cartridges monthly. Ordnance depots palletizing tens of thousands of rockets. Tanker convoys moving fuel. The 9th Air Force, engaged heavily in tactical air support, registered sortie after sortie of high ammunition consumption, an operational tempo that presupposed a manufacturing base to keep it sustainable. Without that supply, tactical innovation would have been brittle. With it, tactics hardened into a strategic advantage. The Thunderbolt's variants illustrate the factory's ability to respond to operational needs. The P-47D, the most common variant, served as the workhorse early in the European campaign. As the war's geography and operational requirements shifted, so did production priorities. The P-47N, engineered for extended range with revised fuel systems and modified wing assemblies, was the answer to the Pacific's vast oceanic distances. Shipping lanes of engines and parts, the retooling of jigs, and the retraining of line workers allowed Republic and its subcontractors to pivot and turn out tweaked assemblies in relatively short order. The P-47M, a high-speed late-war variant with aerodynamic tweaks and more powerful engines intended to counter the Luftwaffe's high-speed threats, exemplified another industrial truth. Factories that could iterate design swiftly translated tactical feedback into new material capabilities. Each iteration required the shop floor to adjust. Wing hardpoints had to be reinforced to carry rockets. Fuel plumbing had to be measured and installed with the same meticulous care as gun belts. A factory that could produce 500 planes a month in Evansville by 1944 did not do so by accident. It did so by planning labor, balancing shifts, changing tooling, and routing engineering changes through a pipeline that minimized downtime. The result was a form of manufacturing elasticity, an ability to change the product without stopping the flow. Combat produced its own evidence that factories were making a difference. On August 17, one of the dates cited in wartime records for large bomber and escort actions, P-47s were part of the force that clashed with Luftwaffe units over critical targets. When concentrated fire met the Luftwaffe formations, the compositions of the losses told a story. Splintered tails, burned-out cockpits, engines hit and failing. Gun camera reels, when debriefs compiled them, provided a visceral ledger. Planes shredded by .50 caliber streams, enemy pilots forced down, and material attrition that the Luftwaffe could not indefinitely absorb. Those engagements amplified a strategic dynamic. Attrition in the air, when met by relentless production on the ground, yields a cumulative advantage. The psychological dimension of this attrition was not negligible. Early captured German commentary sometimes dismissed the Thunderbolt as a slow, heavy brute. But as months passed and losses accumulated, the tone shifted from mockery to apprehension. Stories circulated. German pilots returning to base having to explain why a nimble fighter had been surprised by an opponent that did not indulge in turning fights, but struck like a trap. post-war reflections by some Luftwaffe figures, including widely cited recollections attributed to senior pilots, suggest a begrudging respect for the aircraft's effectiveness and, more pointedly, for the industrial might behind it. It is important to stress the caution the archival record demands. Precise attributions and wording of such reflections vary across sources, and where transcriptions are uncertain, some names and quotations remain undefined in archival notes. The strategic lesson, however, remains clear. When a combatant cannot match the rate of replacement and repair, the pressure of cumulative loss reshapes both morale and capability. Of all the strategic shocks, Operation Bodenplatte on January 1, 1945, stands out as an acute test. The Luftwaffe's surprise attacks on Allied airfields sought to destroy aircraft on the ground and turn back Allied air superiority. In some places, the strike achieved local success. Aircraft were burned where they sat, lines of fighters left in smoldering rows. Yet, the industrial machine reacted. Within 48 hours in some sectors, fresh aircraft were marshaled to airstrips, engines tested, guns loaded. Planes that in peacetime would have taken weeks to produce were, through a combination of existing inventory, expedited assembly, and logistical prioritization, put back on the line. That speed was not universal nor automatic, but it was sufficient to blunt the strategic impact of a tactical surprise. Factories like those in Farmingdale and Evansville, plus depots and transport networks, provided a buffer. The ability to replace material losses faster than the enemy could convert them into a lasting strategic advantage. The replacement cycle, however, had a cost, and with human limits.
Pilots could not be turned out as quickly as aircraft. Training competent aviators remained a time-consuming process. The factories, therefore, competed in a larger ecosystem where metal could be replaced faster than skill. This imbalance became crucial. Attrition forced choices: where to risk aircraft, where to conserve pilot lives, and how to prioritize missions. The Thunderbolt's ruggedness and repairability reduced some pressures by returning damaged aircraft to service, and by making repairs less onerous than total losses. But the human toll of attrition remained central to the war's moral ledger. On the front, Thunderbolt pilots refined techniques that exploited the P-47's strengths. Strafing runs demanded nerves and exactitude. To attack a column of trucks, a pilot had to set approach speed, aim the convergence, and fire in short, devastating bursts to avoid overexposing the aircraft to ground fire. Rockets added a standoff option. Fired from a few hundred yards out, they could fragment a vehicle or disable a bridge with less exposure time. Combat reports and pilot recollections cataloged the brutal choreography of these attacks. The flash of hits, the smell of singed fuel, and the crunch of debris. When a column was broken, when a bridge went down, the effect could be immediate and disproportionate. Trucks stuck, reinforcements delayed, supplies halted. The Thunderbolt's role in interdiction was not glamorous the way a single aerial duel could be, but its cumulative effect on the enemy's mobility and logistics was profound. That cumulative effect is visible in the attrition ratios of the late war. The Luftwaffe, already strained by fuel shortages, pilot turnover, and damage to its industrial base from strategic bombing, found itself on a defensive footing. The Allies, conversely, could convert strategic air superiority into operational pressure through sustained tactical air attacks. The Thunderbolt, durable and heavily armed, became a key instrument of that pressure. It was not invincible. Many P-47s were lost to flak, to fighters that caught them at low energy, and to mechanical failure. But the ratio of repairable damage to catastrophic loss, combined with the factory's ability to produce replacements, altered the operational math. The Pacific theater presented separate but related challenges. Vast oceanic distances forced design and logistic adaptations.
The P-47 and variant's extended-range tanks were not mere accessories. They were structural changes requiring new production patterns. Line workers on the shop floor had to learn modified assembly sequences. Different wing spars, new packings, altered fuel routing, and inspectors had to sign off on revised clearances. The factory's capacity to produce dozens or hundreds of modified airframes while maintaining throughput for theater-specific needs was itself a strategic advantage.
When the Pacific finally surrendered to the weight of Allied logistics and joint operations, part of that pressure derived from a manufacturing system that could outfit aircraft for long-range missions across the ocean. Beyond the tactics and theater-specific adaptations, the Thunderbolt's wartime record left artifacts, literal material tokens of a vast industrial effort. Gun camera reels, saved and declassified, show the verbal shorthand of combat in grainy frames, tracer streams, impact bursts, and the shock of an enemy fuselage coming apart. Those reels were used for debriefing, but later became historical evidence, raw, sometimes gruesome documentation of what the factories enabled. Spent .50 caliber casings, countless in number, clustered in dumps and firing ranges, bear witness to the scale of consumption. Entire crates of ammo represent the monthly output of arsenals like Lake City. And surviving airframes, later restored and displayed in museums, bring visitors face to face with the physical dimensions of the machine. The breadth of the wing, the heft of the radial engine, the thickness of armor around the cockpit. On the restoration floors of museums today, volunteers and technicians deal with the same details that once mattered on an assembly line. Rivet patterns, correct paint livery, the right wiring cloth, period-correct buckles and placards. A P-47 that sits gleaming under museum lights was once the result of a pipe of processes. Procurement, stamping, riveting, balance testing, engine run, the final paperwork. Seeing one restored in a museum reconnects the visitor to that chain of events. Aircraft and heritage collections are not mere memorials to machines. They are repositories of stories about the thousands of hands that made them and the thousands of sorties they flew. There is a peculiar intimacy in the objects left behind from the war. A single spent cartridge telling the story of one gun firing one brief burst. Ripped fragments of cowling in a collection that match an archival photo of a specific engagement. A crew chief's logbook listing times, maintenance entries, and remarks about damage. All of these piece together a humanized ledger of industrial warfare. Gun camera footage sometimes captures a pilot's last clear view of an enemy aircraft before being hit himself. The stills taken from those reels are both analytic tools and moral artifacts. They make concrete a violence that was otherwise abstract at the level of production statistics. The numbers of planes, the rate of output, the monthly production figures. That very concreteness drove a change in doctrine and psychology on both sides. The Luftwaffe, encountering a steady tide of armored, well-armed fighters, had to reckon with a foe that could take punishment and still be repaired or replaced. Attrition wore down not just material reserves, but morale and the luxury of tactical experimentation. The Allies, conversely, found that industrial redundancy allowed riskier mission profiles that, taken together, produced strategic pressure on supply lines and troop movements. Consider the image of an airfield after a raid. Scorched patches where fuselages once gleamed, oily puddles under wrecked engines, the slow smoke of a burned-out wreck. Now imagine, 50 miles away, a factory where men and women who knew nothing of the site on that field were running shifts to install starters, check propellers, and lace harnesses. The temporal and geographic separation between destruction and replacement is one of the defining features of modern industrial war. That separation is not moral insulation. It is the reality of distributed labor supporting concentrated violence. The story of technicians and crew who rebuilt Thunderbolts between missions deserves attention. Field depots learned to swap complete assemblies in days. A damaged wing was sometimes replaced with a serviceable spare. Damaged avionics were pulled and placed in new housings. The logistical readiness to perform such swaps depended heavily on factory throughput and spare parts inventories. Without that steady feed from factories, the tempo of operations at the front would have slowed drastically. The ability to move parts quickly, to triage which aircraft were worth repair, and to manage supply chains in devastated theaters separated victory from stalemate. In some cases, the aircraft themselves became a sort of psychological weapon. The thunderous drone of a formation passing overhead, the sight of rockets arcing toward a convoy, the whistle and shudder of heavy machine gun barrages. Soldiers on the ground often cited the sound of P-47s as an omen of impending attack or relief, depending on allegiance. The sensory linkage between factory and front, the rivet gun's percussion and the P-47's roar, remains a resonant image. Sound bridged production and combat, a kind of acoustic continuity from the assembly bay to the combat box. There are, too, quieter stories of ingenuity, field modifications that later became factory directives. Pilots and ground crews improvised armor, jury-rigged fittings, and altered fuel management techniques. These field solutions would sometimes be fed back to production engineers, prompting revised assembly procedures. The loop from frontline feedback to factory floor implementation was not instantaneous, but it existed. It mattered. It converted combat experience into production instruction and production instruction into the next generation of machines. By late 1944 and into 1945, the weight of production had shifted decisively. The Allies' manufacturing base, energized by mass production techniques and an all-encompassing logistics system, produced a flow of aircraft that hardened their operational options.
The Luftwaffe's situation deteriorated under combined pressures. Strategic bombing of armament factories, loss of experienced pilots, fuel shortages, and the sheer accumulation of Allied aerial interdiction. The Thunderbolt was only one element of this larger story, but as a concrete instrument of tactical power, it symbolized a new equation. Manufacturing capacity plus adaptable design plus battlefield feedback equaled decisive operational pressure. When the war ended, the physical remnants scattered across the globe became testimonies. Museums in the United States and Europe acquired P-47s preserved in varying states. Some restored to flying condition, others preserved as static displays. Gun camera archives, transferred from classified files to public repositories, became rich sources for historians and documentary makers. Spent shell collections and ordnance inventories, once classified for their sensitivity, now serve educational purposes, allowing scholars to quantify and visualize the scale of material expenditure. These artifacts help explain how a factory full of rivet guns and crates of parts could, day after day, create a thunder that altered battlefronts. There is an ethical dimension to revisiting these artifacts. Each polished fuselage in a museum glosses over the fatigue, hazard, and human cost embedded in its construction. The makers, often young, often pressed by wartime urgency, faced long shifts, hazard, and the constant knowledge that mistakes had lethal downstream effects. Accepting the pride many felt over production achievements does not absolve the moral calculus of wartime labor. The documentation, payrolls, training rosters, safety logs, showcases both the organizational brilliance and the human strain of mass production. The post-war historiography and veterans' recollections add layers to the story. Some German aviators' memoirs and interviews reflect a grudging admiration for Allied industrial output. Others lament the strategic missteps within their own structures that made them vulnerable to sustained pressure. Again, archival caution is necessary. Not all attributions are clean, and some names in surviving transcripts remain undefined or unclear. But the thematic arc is robust. Production capacity ultimately changed what could be done on the battlefield, and that change had both strategic and human consequences. Return now to the assembly bay you first imagined. The scene has not lost its edges. The rivet gun staccato, the breath fogging as workers move between heated interiors and the ambient hall, the careful placements of wiring, the crates of spare parts. These remain the origin point. The factory is where material decisions transpired, where an engineer's calculation met a worker's hand, where plans for armor and fuel tanks were translated into hammered skins and balanced propellers.
The coldness you felt as an evocative reconstruction still frames the narrative because it helps you imagine the sensory world in which these decisions were embodied. But the essential fact is not the temperature. It is that in these industrial spaces, people turned raw materials into a kind of leverage that, when projected across oceans, became a decisive factor in a global conflict. In the months after hostilities ceased, planes were mothballed, scrap lists compiled, and production lines repurposed. Factories that had been throbbing at a wartime cadence shifted toward peacetime production or closed their doors. Former line workers returned to civilian life, carrying unique skills into an economy that would soon boom with new demand. Some of the thunderbolts that survived the war found second lives, on display in the air shows of later decades or in the gentle care of restoration hangars. Those restored aircraft, when flown today, provide pilots and audiences alike a visceral connection to the past. The throttle's bite, the R-2800's rumble, the hand on a metal control stick. They are living links back to a time when factories produced not only machines, but operational concepts, doctrinal shifts, and an industrial rhythm that reshaped modern warfare. The Thunderbolt's legacy is therefore twofold. Technically, it marks a moment when engineering choices, armor, turbocharged power plants, concentrated armament, yielded a platform adaptable to multiple theaters and missions. Industrially, it represents the capacity to produce and iterate at scale. Strategically, it demonstrates how redundancy and replacement can transform attrition from a poison into a manageable cost. Humanly, it memorializes the workers and crews whose labor turned plans into planes and whose resilience under pressure made operational innovation possible. In the end, perhaps the simplest way to sum what those factory bays built is this: they forged not merely a machine, but a modality. The Thunderbolt embodied a shift toward weapons designed with an eye not just to performance, but to survivability and producibility. Toward tactics that leaned on numbers and sustainment as much as on individual aerial virtuosity. The thunder in its name is both literal and metaphorical, the sound of radio power and the reverberation of industrial force across theaters of war. So, when you stand before a restored P-47 in a museum or watch gun camera footage that lingers on a tracer stream finding its mark, remember the assembly bay. Remember the thousands of parts, some sources noting approximately 65,000 per plane, and the miles of wiring stitched through fuselages. Remember the stat that at Farmingdale lines peaked at about one completed P-47 per hour, and that Evansville was producing on the order of 500 aircraft a month by 1944. Remember the ammunition arithmetic. Roughly 3,400 rounds per aircraft at a typical 8-gun loadout, and arsenals manufacturing tens of millions of rounds monthly to keep those guns fed. Those numbers are not abstractions. They are the material foundation of tactics, the logistical sinews of campaigns. And remember, too, the people. The women who learned rivet guns and wiring looms, the machinists and inspectors whose signatures on checklists certified that a plane could fly, the crew chiefs who counted holes and swore at the degree of damage while planning repairs. All of them part of a chain that connected factory floors to the skies where history was made. Their labor remains visible in the rivet lines and in the records, in artifacts and in the stories of pilots like Robert S. Johnson and others whose survival and success were inseparably linked to machines that returned them from combat. As the film of this account edges toward a close, picture one more sequence: an empty bay at dawn, sunlight cutting across aluminum skins.
A finished thunderbolt waiting with its engine capped. Mechanics scribing the final notes into the logbook. A truck arrives with a crate of spare parts. A worker pulls on a glove and reaches to heft a component into place. Outside the hangar, the sky is indifferent and vast. Inside, a finished aircraft sits between the human efforts that made it and the theater that will test it. The thunder it will create belongs as much to the factory as to the pilot. If you've been moved by the way industrial scale met human endurance to reshape air combat, there are places that preserve and interpret this story. Museums across the United States and Europe exhibit surviving P-47s, gun camera archives, and ordnance collections. Restoration groups keep flying examples airborne for new generations to witness. For a closer look at the objects and documents that shaped these narratives, links to museums and primary sources are in the description. Visit them, and you'll see how the Thunder was built, bolt by bolt, belt by belt, flight by flight, inside a factory whose cold, riveting halls became the progenitor of a new kind of air power. We began inside an evocative reconstruction of a frozen bay. We end with the same image because it holds the story in microcosm. The sound of rivet guns and the smell of oil are anchors for a larger truth. Industrial capacity, disciplined labor, and tactical adaptation together changed the sky. The Thunderbolt flew because factories made it fly. The war's air power shifted because those factories never stopped turning. That is what the frozen factory built. Machines, doctrines, and an industrial momentum that echoed far beyond its walls. We began inside an evocative reconstruction of a frozen bay. We end with the same image because it holds the story in microcosm. The sound of rivet guns and the smell of oil are anchors for a larger truth. Industrial capacity, disciplined labor, and tactical adaptation together changed the sky. The Thunderbolt flew because factories made it fly. The war's air power shifted because those factories never stopped turning. That is what the frozen factory built. Machines, doctrines, and an industrial momentum that echoed far beyond its walls.